Hello, hello, you lovely people. I hope you're all doing great. If you're not, then you soon will be, because we're about to do some chemistry. Today we'll start our journey through Unit 2, which is called Nature's Chemistry. And the first key area that we're going to come across is homologous series. Today we'll kick things off in this video by having a little look at fractional distillation and hydrocarbons. And all we need to do today really is to understand the process of fractional distillation, be able to describe it, and be able to describe and understand what a hydrocarbon is as well. So let's have a look at this word hydrocarbon first of all. Now, whenever we come across a word that we might not have seen before in chemistry or in any science for that matter, what I like to do is to kind of try and split the word up into two or three parts and try and address it that way to figure out maybe what it means. And it's probably quite obvious already what this word means. If we look at the first part here, hydro, sometimes we can think in water, but if we think about elements, that definitely sounds like an element that we know, hydrogen. And then the second part, well, no prizes there, that's obviously carbon. So if we wanted to then come up with a definition for this word hydrocarbon, it would quite simply be this: a hydrocarbon is a chemical compound which contains hydrogen and carbon. And here's the most important word in that sentence: only. So a hydrocarbon is a chemical compound which contains hydrogen and carbon only. They're the only elements it has in it. So let's now keep that definition in mind and have a little think and a look at some chemical compounds. So the first little compound I'm going to write out and draw for you is called propane. Now, propane's chemical formula is C3H8, meaning it's got 3 carbons and 8 hydrogens. And if I was to draw out propane, showing all of the covalent bonds, all the carbons and hydrogens bonded together, this is what propane would look like if we could see all those bonds in between the atoms. Now we're going to work our way up throughout Unit 2 to be able to go from just a name like propane to write down its chemical formula, and then to write, as I have done here, the full structure. Now let's look at another chemical compound called acetone, and its chemical formula is C3H6O. And again, if I was to draw out all of the atoms showing the covalent bonds, here's the structure of acetone. Now, boys always know what acetone is. It's used for removing your lovely nail polish at the end of a nice Friday night. Now, back to this definition here. A hydrocarbon is a chemical compound which contains hydrogen and carbon only. Well, if we look at propane, it's got carbon, it's got hydrogen. Acetone's got carbon and hydrogen as well, but propane, that's all it's got. That's all it's got. It's only got carbon, it's only got hydrogen. It's a hydrocarbon. Acetone, yes, it's got carbon, yes, it's got hydrogen, but look here, it's also got oxygen. This is not a hydrocarbon. Another couple of examples of hydrocarbons that we might be familiar with are methane gas. Use a lot in central heatings in homes, using our gas taps at schools, used for cooking, all sorts. Petrol, obviously a very important resource for fueling pretty much the world these days. Diesel as well, another important fuel, and they're used quite a lot, hydrocarbons that is, in the production of plastics. So even if we just take another kind of 4 examples, we can really see the importance of hydrocarbons and why we're talking about them today. Now, if these hydrocarbons are so important, which they clearly are, we need to ask ourselves the question of where do they come from and how do people get their hands on them. And it all comes down to really a raw material called crude oil. Now, crude oil is a very, very thick, sticky substance that's found deep underground. It's a fossil fuel. It's made from the fossilized remains of plants and marine animals. And they use a process called the fractional distillation of crude oil to really break down the crude oil into useful fractions. Now, fractions just mean different parts. Now, why is it important to break down the crude oil? Well, the crude oil itself is not all that useful as a resource itself, but within it, trapped within it, are all these different useful parts or fractions, as they're called. So methane gas is trapped in there, petrol is trapped in there, diesel, kerosene, paraffin, you name it, they're trapped. All these hydrocarbons are trapped in the crude oil, and we need to use a process called fractional distillation to separate out and to really unlock all of these useful hydrocarbons that are trapped within the crude oil. Before we go into any more detail on crude oil and fractional distillation, I think it's important at this point to take a step back and just to remind ourselves about just distillation in general and how it's used to separate different liquids and why it's so important. So distillation is a separation technique, and it's used for separating different liquids. That have been mixed together. Now, these liquids are separated by using the fact that they'll have different boiling points as well. And that's really all that distillation is. It's just using the fact that these liquids have different boiling points, and if we heat up a mixture of liquids to a certain temperature, then different liquids will be boiled off at different rates. Now we can look at a little example on that here. Now this is a diagram of a distillation apparatus that you might see in the lab when we come back after summer. And from the outset it probably looks quite complicated, but as we go through it you'll see that it's quite a simple and quite straightforward method of separation. We've got here at the start a round bottom flask containing a mixture of different liquids. Now this mixture of liquids could be something quite simple like water and maybe some alcohol, and they mix together, and we're wanting to extract the alcohol from the water. Now if we think back to our little definition of distillation that we just wrote down, it is the separation of different liquids using different boiling points. So we should be comfortable with the fact that water's boiling point is 100 degrees C. Now alcohol's boiling point is around about 78 degrees C. So if we use something like an electrical heating mantle to heat up this mixture, let's say we heat it up to 85 degrees, then we wouldn't expect all the water to be able to boil, but all of the alcohol will be able to boil and turn into a vapor. And that's exactly what would happen. If we heated up this mixture to 85 degrees, the water wouldn't be able to boil, but the alcohol could. And the alcohol will turn into alcohol vapor, a gas, and travel up the tube here and be forced into the next section of the apparatus, which is called the condenser. And it does exactly what it says in the tin. It condenses the alcohol from a gas back into a liquid. And how does it do this? Well, it uses, I should say cold, it uses cold water to cool the gaseous alcohol back into a liquid. This condenser is a hollow tube where the alcohol vapor will enter, and around the outside of the tube we've got our cold water running in and keeping it nice and cold. And if we reduce the temperature to below this 78 degrees, the alcohol will turn back into a liquid and it will start to drip out and collect in our collection flask at the end. And what we'd have is no longer a mixture of water and alcohol, but we'd have now a lot purer sample of our alcohol that we wanted to obtain. Now let's take things back to the ideas that we talked about at the beginning of the video, crude oil, hydrocarbons, and apply the exact same principle that we just did with the alcohol and the water to the crude oil. Now if you remember, I said that crude oil itself isn't all that useful, but within it, trapped within it, are all these different fractions, all these different liquids that have been mixed together that need to be separated. So how can we separate them? Well, we'd use distillation, but in this case we would use fractional distillation. And the reason that we call it fractional distillation of crude oil, not just distillation, is to really try and emphasize all of the different fractions that are held within the crude oil. We've got diesel, petrol, methane gas, propane. There's fractions that are even used for making tarmac on roads to turn into plastics. There's so many useful fractions, and if we use distillation to get these different fractions, then we call it fractional distillation. Let's get a definition down now for fractional distillation. So fractional distillation is just the separation of a raw material, crude oil, and separating crude oil into different and useful fractions. So that's all that fractional distillation is. It's the separation of crude oil into these useful fractions that we've just talked about. So just like we did with the simple distillation apparatus where we took a closer look at how the alcohol was removed from the water, we're going to take a closer look at fractional distillation as well and look at how these different fractions are separated. And they're separated in something called a fractional distillation column. And we'll have a little look through that in just a second. But before we do that, I want us to just look at some kind of key terms and words that we're going to use to describe some of the trends in the fractional distillation column. And we need to just be familiar with these terms and words before we go any further. Now, the first key word that we're going to have a little look at here is viscosity. Now, viscosity is probably going to be a new word to quite a few of you. Now, simply put, viscosity is just a measure of how thick or runny a liquid is. So if we think about something like water, we would describe water as having quite a low viscosity. It's not very thick at all, and it runs quite easily. Whereas on the other hand, if we took a liquid like honey, then we describe honey as having a high viscosity, and that's the way I remember it. I write this down. I say hi honey, and that's what I say. So when I come home from work, I open the front door, say, "Hey honey, I'm home," and then I'm just greeted by silence because I live alone. But hi honey is the way that I would use to remember viscosity. Honey has a high viscosity. It's very thick. It's runny. It doesn't pour very easily. Whereas, as I said, something like water with a low viscosity is just quite thin and it runs very well. It's easily poured. Now, the next keyword that we need to know for our fractional distillation column is probably one that's going to be a little bit more familiar to you than viscosity was, and that is flammability. Now, the flammability of a substance is the measure of how easily a substance will burn. And our last key phrase is one that we've already looked at before and we're probably quite familiar with, is boiling point, but it's worth just to get a little definition down here anyway. Now, the boiling point is the temperature at which a liquid will boil or turn into a gas. Now, I wanted to highlight these three definitions because we're going to use them in just a second to describe different trends in the fractional distillation column, which is where we use crude oil and separate it into different fractions. So we're going to use these terms for viscosity, flammability, and boiling point as descriptive words, so we need to know what they mean. So here's a diagram showing the fractional distillation column used for the fractional distillation of crude oil. Now, we've got here our crude oil barrel, which has been sucked out of the ground by some oil rig. And within the barrel, we've got our mixture of different hydrocarbons, but they're all mixed up. We want to separate them into different fractions. So what they do is they pour the crude oil into a column just like this one, and using heat, just in the same way that we heated up our water and alcohol mixture, we can separate this mixture of hydrocarbons based upon their different boiling points. So if we have a little look at the column, there's lots of different exits on the column where we're getting out our different fractions. At the top we'll get our bottled gas or methane gas, petrol, then paraffin, diesel, etc., all the way down to stuff at the bottom called residue or bitumen, which is used for tarmacking roads. Now you'll be glad to know that you don't need to remember all of the different fractions coming out of this column, and you don't need to remember the uses for the fractions. I highly suggest though remembering the last or bottom fraction and the top fraction, because if we remember what these two are, we can infer and we can figure out all of the different trends associated with the column, and that's all we need to know. We just need to know the trends. And what are the trends? Well, there are four key trends that we need to be able to talk about and discuss when thinking about the fractional distillation column. We need to know the trend in the size of molecules as we go down or up the column. We need to know the trend in boiling point as we go down or up the column, and we also need to know the trend in viscosity and flammability as we go down and up the column. So let's flick back and we'll have a little go at drawing this column and think about these trends. So here we've got our fractional distillation column, and into the column, as we know, we put in our crude oil, and the column gets heated up and the crude oil is separated into our different fractions like methane gas, petrol, diesel, residue. Now the first trend we're going to want to have a little look at here between these fractions and within the column is the size of the different fractions. Now in order to do that, we're going to have a little look at the chemical formula for these four fractions. Methane gas is CH4, petrol is C8H18, diesel is something like C15H28, and residue we'll just call it C30H60, roughly something like that. Now if we look at the sizes then between methane, petrol, diesel, residue, etc., there's a clear trend. As we go down the column, the size of the molecules increases. There's our first trend. Nice and straightforward. As you go down the column, the size of the molecules increases. And that kind of makes sense. Methane gas, stuff that comes out the gas tap. Remember I said just to kind of really remember the first and last fractions, and that will help you remember these trends. Compare gas to residue or tarmac, a road. What do you think is going to be a smaller molecule? A molecule that floats in the air, can move around quite freely, or thick sticky tarmac? It's quite intuitive which one is going to be the bigger molecule. Let's have a little think now then at the second trend that we need to appreciate and understand for our fractional distillation column and for the fractions that are produced. The next trend is the boiling point, and in order to appreciate the trend in boiling point, we need to come back to the fractional distillation column itself and understand the difference in temperature throughout the column. So the column is heated at the very bottom. Heat is applied to the bottom of the column. So it makes sense then that at the bottom of the column we've got the hottest part of the column, and therefore at the top of the column, where it's furthest away from the heat source, it would be the coolest part of the column. And so if we're getting methane gas produced at the coolest part of the column, the coldest region, it then implies that it must have a pretty low boiling point, because remember all these fractions are coming off because they're being boiled away. If we've got residue only able to boil at the hottest region, that would then imply that it's got a very high boiling point. And so our trend in boiling point must be the exact same as our trend in size. As we go down the column, the boiling point will increase from low to high. And again, let's go back to what I said before about just remembering two fractions. If we remember that methane gas is produced at the top, the coldest region, and residue at the bottom, then that makes sense with remembering our boiling point. Methane gas is a gas at room temperature. It boils at something like minus 160 degrees. It's going to have a very, very low boiling point. Whereas residue or tarmac, stuff that we use on the road, that's not going to boil very easily. You don't want a road that's going to boil away in a hot day, so that's going to have a very high boiling point. So again, if we just remember these two fractions, we can infer most of our trends. So let's come on to our third trend here and reintroduce this word that we talked about earlier, viscosity. Can you remember what it means? Well, it is the measure of how thick or runny a substance is. Now let's have a little think about our different fractions. We've got methane gas, petrol, diesel, then at the bottom this thick sticky residue. What's happening to the thickness of these materials as we move down the column? Well, petrol is quite similar to water. It's very, very runny, flows very easily. Diesel compared to petrol is a little bit thicker, doesn't run as well, and then at the very bottom we've got stuff like tarmac, thick, sticky, gloopy. Well, what's happening to the viscosity then as we go down the column? Well, it's the exact same as what we've seen in our boiling point and in our size. As you go down the column, the viscosity of the different fractions will increase as well. They're getting more and more thick, they'll be less able to be poured, the viscosity is increased. Now let's look at our fourth and final trend that we can hopefully just squeeze in at the side here, and we're looking at our flammability of the different fractions and how does that change as we go down our fractional distillation column. Well, let's think about our different fractions like we did before. Methane gas, we've experienced that before. If you take a match and expose it to methane gas, like that comes at the gas taps at school, it's going to go on fire very, very rapidly. It's a very, very high flammability, methane gas. Easily burned, very easily burned. Petrol too, it's pretty high. If you put a match next to petrol, it's going to go on fire. So will diesel, but it won't burn as well diesel as petrol. And then if we go down to the bottom and think about our tarmac, our residue, if you put a match on the road, will the road go on fire? I doubt it. It's going to have a very, very low flammability. So again, just think about those first and last fractions. Methane gas comes out the gas tap. You take a match to it, it is going to go on fire instantly. If you put a match in the road will not go on fire. So think about that first and last fraction, and that will help you with all these different trends. So our final trend here, flammability, is the kind of odd one out. It does not increase this time as we go down the column, it instead decreases as we go down the column. So those are our four trends. This is what we really need to be able to appreciate from our fractional distillation column. How does size change? How does boiling point change? How does viscosity change? And how does flammability change? And I think that's probably quite a good place for us to end the video there. I hope you've enjoyed it. I hope it's been informative, and I look forward to making some more for you in the near future.